For the next part of Module 5, we'll take a look at dimensional measurement statistics, and we'll do a tutorial that asks how many measurements are required to have a certain confidence interval. So for pump shaft length L2, we'll seek to identify the number of measurements required to reduce our confidence interval to plus or minus 0.01 millimeters. Recall previously that the student's T can be used to help us estimate the true mean of our sample, taking our sample mean, multiplying student's T times our standard error, and that gives us, for a given probability, a range within which we can expect our mean to lie. More specifically, we call that a confidence interval when we use the standard error, and the standard error is simply the standard deviation of the sample divided by square root of n. So how do we use that to answer this question about measurements? Well, first we note that the interval is two-sided, so it's a plus and minus range, and so our confidence interval is a range that we can divide in two and define that as student's T times standard deviation over square root of n. If we just do a little algebra, we can solve for n, the number of samples. And in so doing, we can see n approximately equals student's T for given degrees of freedom and a given probability times the standard deviation of our sample divided by D, the precision value for our confidence interval, and squared. And so what we note, though, from that is that student's T is dependent on n, the number of samples. So we really need an iterative guess and check method to answer this question. This type of question is in the family of design of experiments, and it really has to do with identifying the sample size for our desired result. L2 is that measurement from the end on the end of the shaft to the middle of the shaft. It's supposed to be 52 millimeters. Previously, we took a sample, and the sample size was 10. So here are some of the example measurements shown here, ranging in the 52, 51 range. We also took a look at precision intervals and confidence intervals. So the precision interval answers the question, if we were to take more measurements based after our sample, what's the range of 95% of the measurements likely to fall within? That's the precision interval. Slightly different, using the standard error of or the standard deviation of the means, is the confidence interval, where it's defined here. And in this case, we found that the confidence interval on the upper side was 52.246 and the lower side was 51.985. If we take that range and split it in two, that basically says that our confidence interval range is 0.13, which is quite a bit higher than our goal. So some of the things that we recognize here is that we had a sample size of 10, a student's T that corresponded to that of 2.262, which was based on a degree of freedom nu of n minus 1 or 9. And we also had the sample average and standard deviation here. So we're going to need to use student's T's table again, but this time we need to look up, guess a certain sample size, look up the student's T, compute n from that equation, see if they match, and do that iteratively. So generally what we're going to do is walk through a process where we specify D, and then we guess different n's, use the student T associated with that degree of freedom, and then we see at what point we have the appropriate number of samples to get to the precision value that we're looking for. And we can do that not only for a very small value, 0.01, we could also do the same thing for the question of, given that we just had 10 samples and a confidence interval of 0.13, what if we wanted to know how many samples it took to cut that confidence interval in half to, say, 0.065? So with that, we will go ahead and look at the data. Okay, and the data of the original responses from the form is shown here. We took a sample of 10 for pump shaft L2, previously shown, and we also looked at confidence intervals here. So how do we go ahead and do this? Well, let's go ahead and get some of our equations up here. And first we'll start out with a guess of n. So we'll call this guess of n here. And we'll say 20. Well, how many degrees of freedom is that? So let's call that DOF or nu right here. Well, DOF is just this value minus 1. Okay. Well, then what's the student's T for 95% probability? So with student's T for 19, we can look that up in our student's T table, come down here and find 19, and that equals 2.093. So we can come back over here, pop that in here. Okay, so our desired D, so desired D, we'll put right here, and we'll call it 0.01 units of millimeters. We'll just give it a little highlight so we know what we're looking for. And then our sample size we can approximate as T times standard deviation divided by D and all squared. So we can see what we get from that. So let's take the T that we have here, multiply by our standard deviation, which is right up here, and then divide by our D right here. And then we square that. And we'll go ahead and we'll lock in dollar signs, these guys, so we can move our calculation around. And so we see that we'll get this down to integer form here. And this N, 1459, doesn't agree with our guessed N, 20. So that's not going to work to get us down to a confidence interval of 0.1. Let's try a bigger number. How about 50? So for 50, we have 49. We can look that up in our student's T table. And over here, we see that this table is truncated a bit. So let's go over to this other table, which we calculated a bit more with the functions in Excel. So this is 2.01. And so we pop this in here. And then again, we're getting smaller, but this isn't even really close. Let's try another one, 100. So 100 gives us a degrees of freedom of 99. And 99 leads to 1.984. And getting smaller, but not really that close. So let's jump up quite a bit with our sample size. And we'll take a look at sample size of 99. And so then we'll go over to our student's T calculation here and see. Let's go to the bottom of this table. Well, we don't even have 999 here. We only have up to 200. So we got to figure out what we're going to do with this. Well, with the student's T functions in Excel, we can calculate them for 95% or 90, 99% using the t.inv.2t function. So I'm just going to take this section right here and I'll copy it and move it right back over into here. And I think I'll pop it right up in here. And so with that, we can see, for example, if I put in 99, right here, we get 1.984. And if I put in 999, doing all right there. So we'll go ahead and we'll just make this a little different here so we can see what the coloring is. So 999 gives us 1.962, and we can pop that in here, paste it as values, and see if our N on this side is close to N on this side. And it's closer, 1,000 to 1282. So that means that we're approaching the number of samples required to get 2.01. But one thing we should note is this number is not really getting that much smaller. I could put in here, let's say 10,000, and this is still just 1.960. Okay. So, this value right here, we'll call it, let's put a T right here. We'll say this equals this minimum value that we're using right here. It's not getting much smaller. Okay. 1200, try that. So one of the things we could do is we could just go ahead and say, since T isn't really now a function of N, let's see what happens if we just solve for N using the equation that we had here before. We'll again use this T value, multiply times the standard deviation, divide by D, and then square it. And this is going to just tell us, what the actual number is for the number of samples required to get to that confidence interval. So 1282 is specifically what we're looking for. So we could come over here and put 1280, let's put 1281 right here. And we can put 1281 in here, 1281. That's going to be, 1282 will give us 1281 degrees of freedom. And then we can just use 1.962. And we can see that, in fact, this number and this number are in agreement. Okay, which means that we've iterated successfully. So that's a bit of a clunky kind of manual process, but it technically is getting the job done in terms of helping us identify the number of samples. So in truth here, we would say that we need 1282 samples to reduce CI to 0.01 millimeters with 95% confidence. And we should also say, big assumption, that we are assuming a normal distribution. And we're assuming that the sample standard deviation is the same as the population standard deviation, which may or may not be correct. And we'd have to check that after we increase the sample size. So 1,282 samples, is that reasonable? It might be, depending on the application. It might just be too many. And we might say it's going to be, we're going to have find other ways to reduce our confidence interval. One simple way would be to reduce the standard deviation. And that probably could come through manufacturing quality control, manufacturing processes that we tighten up, or even measurement practices that we tighten up and get more repeatable. Another look at this same problem is to say, okay, if that's too many, what might be more reasonable? What if we changed D instead of D to 0.01? What if we said we're just going to be half of current interval? And so that half of the current interval is 0.065 is our precision value for our confidence interval that we're looking for. And so we can see from some of these numbers that this and this guy still don't quite match. We might find, we'll insert a row above here, might try 30 and see what we get for that. So we can go ahead and come over here and say, well, what about 30 or 29? And with 29, we have a degree of freedom of 2.045, and 33 and 30, these are the two numbers that we're looking at. They are not quite the same, so we can try another one. We could try, maybe, let's go up a little bit, try 35. And so with 35, we'll have 34, put this guy here as 34. That gives us a D of 2.032. And we can see this guy's 35, this guy's 32. Not quite the same. Maybe we'll split the difference. Find 33, and then we'll specify 32 as the degree of freedom here. 2.037. And we can see that these two, 33 and 32, are as close as we're going to get with the tolerance that we have here. So to get to reduce the confidence interval in half to 0.065, we need to take 33 measurements, or let's call it 33 samples. So that is how that kind of problem works, and hopefully it's useful in constructing a measurement or experimental test for a quality control program, particularly when it comes to measuring geometric tolerances with a manufactured part.